Hello everyone. In this video, we are going to discuss valence bond theory with reference to explaining bonding in coordination compounds. This is a topic in class 12 chemistry chapter coordination compounds. I am Anandavalli from Guidance Education channel. Before we start the topic, please watch the video completely so that you get all points clear. And if you think the video is useful, do like the video, share the video with your friends, and also leave your feedbacks as comments in the comment box below. If you're watching without subscribing my channel, do subscribe it now and support me. Your support is my motivation. Also, press the bell button and all button near it so that you get intimated as soon as new videos are posted. Thank you very much. Let us start the topic. Coordination compounds are compounds of D block elements. They have the D block elements as the central metal atom. Bonding in these compounds need more explanation. Coordination compounds are complex molecules. Therefore, their structure or their bonding cannot be explained on the basis of the conventional ionic or covalent bonds. Ionic bond or the electrovalent bond and the covalent bond can successfully or more effectively explain the structure of molecules wherein the atoms participating in the bond formation have only 8 electrons in their outer orbitals after bond formation. That is, these two types of bonding stresses on octet rule. But what about the case of those compounds wherein the central metal atom has more than 8 electrons in its outermost orbital after bond formation? So, other concepts are put forward to explain this, like Werner's theory, valence bond theory, crystal field theory, ligand field theory, molecular orbital theory, etc. In your syllabus, only Werner's theory, valence bond theory and crystal field theory are dealt with. We have already discussed crystal field theory. In this video, we will discuss valence bond theory. You have already learnt hybridization and valence bond theory in 11th standard. All the basic points you have already learnt there. Anyway, valence bond theory utilizes the principle of hybridization. Hybridization is the intermixing of orbitals of near energy level to give rise to degenerate orbitals. In the case of coordination complexes, it is the near energy level orbitals of the central metal atom which undergo hybridization. The aim of hybridization is to produce just the required number of free orbitals wherein the ligands can donate electron pairs and get bonded to the central atom. As you know, the central atom in the coordination entity is the D block metal. The number of the period is noted by the letter N and the D subshell will be N minus 1. That is, for the fourth period D block elements, their D subshell will be 3D, that is 4 minus 1. Similarly, for the subsequent periods as well. Hybridization in the D block metals may take place in two different ways. The inner orbital N-1D, the NS and NP might hybridize. Only the required number of orbitals, that is orientations, will take part in hybridization. That is, for the fourth period elements, some of them might undergo hybridization like this. Required number of D orbital orientation, that is 3D, 4S and 4P will take part in hybridization to give rise to the required number of hybrid orbitals which are degenerate, or the outer orbital D, that is ND, NS and NP. Here also only the required orbitals or orientations will undergo hybridization. For example, 5D, 5S and 5P or 4D, 4S and 4P. Let us take one example in order to understand this. I will explain step by step. Take the example of hexamine cobalt 3 plus ion complex. Cobalt is the central atom. Though it has a charge of 3 plus, its atomic number does not change. It is 27. It has 3 electrons less. Atomic number is on the basis of number of protons. It doesn't change. I will explain the orbital picture of cobalt 3 plus ion before and after hybridization. For cobalt ion, we need show only 24 electrons. Argon 18. Then we have to show 6 electrons. The further orbitals are 3d, 4s and 4p. D orbital can accommodate a maximum of 10 electrons. So all the remaining 6 electrons can be shown in the 3d orbital. Only one orbital has paired electron. So this is the structure of cobalt 3 plus ion. During hybridization, 2 electrons from the half-filled orbitals of the d subshell get shifted to the other 2 half-filled orbitals, making them paired. Now, 2 of the 5 d orientations are free. They are empty. These 2 orbitals, 4s orbital and 4p orbitals, get mixed up, forming 6 hybrid orbitals of same energy level. So altogether there are 2 plus 1 plus 3 equal to 6 orbitals free now for accommodating the ligands. In this complex there are 6 ammonia molecules which are neutral as ligands. So in this method 6 hybrid orbitals are formed. This is the orbital diagram of the cobalt 3 plus ion after hybridization. You have to also include argon 18 in the orbital picture diagram. I have not shown it there. Now we will show the linking of 6 ammonia molecules. In ammonia, there is one lone pair. 3 electrons are attached to the 3 hydrogen atoms. This is the lone pair on the nitrogen atom. Lone pair of each of the 6 ammonia molecules will be donated to the free orbitals of the central metal atom, thus binding the 6 ammonia molecules to the central metal atom. The charge on the central metal atom will remain as such, that is 3 plus. So that is the structure of the hexamine cobalt 3 plus ion complex. The number 3 in its name refers to the oxidation state of cobalt in this compound. Cation complex can now accept 3 chloride ions, that is chlorine atoms having 1 negative charge each, to form hexamine cobalt 3 chloride compound. Bonding with the chloride ions will be ionic in nature. From the orbital picture, you can see that there are no unpaired electrons. All the electrons are paired. Therefore, the compound is diamagnetic in nature. So, this helps to explain the diamagnetic property of this octahedral complex. As the inner 3d orbitals take part in hybridization to make 6 degenerate orbitals to accommodate the ligands, this compound belongs to the inner orbital or low spin complexes. I hope the video was of great use to you. Do not forget to subscribe, like, share and leave your feedbacks as comments in the comment box below. Also press the bell button near it so that you get intimated as soon as new videos are posted. Thank you very much. In the next video, we will discuss paramagnetic coordination entities. Thank you very much. Bye for the present.